Week 3, Data Transformation in Data Mining. Welcome to Week 3. This lesson is all about making data ready for analysis. You will learn about feature normalization, encoding, and scaling. These techniques are used every day in real-world data science and AI. Ready to get started? Running the cell now. Let us make sure our output is easy to read by hiding warning messages. We hide any warning messages before we begin. This helps you focus on important results. Import NumPy as NP. We set the random seed to 42 for reproducibility. Running the cell now. This code sets a random seed and suppresses warnings to ensure reproducible and clean outputs in data transformations throughout this lesson. Notice that no output is generated here. Its main purpose is to establish a consistent and distraction-free environment for learning feature normalization and scaling. This foundational step helps avoid unexpected variations in your data results as you apply transformation techniques. What is data transformation? Data transformation prepares raw data for machine learning. Real-world data comes in different shapes, formats, and scales. We use transformations to clean and standardize inputs, convert text or categories to numbers, adjust values to a common range. Well-prepared data helps models understand and learn better. Running the cell now. Let us load the Titanic dataset. This dataset contains information about passengers, such as age, gender, and survival. We import pandas to work with tabular data. We load the Titanic dataset from an online source. This dataset is used for many machine learning projects. We check the number of rows and columns. We look at the first few records to see what the data looks like. Running the cell now. This output shows the raw Titanic dataset with 891 rows and 12 columns, confirming the data's initial shape. The first 3 rows illustrate key features like passenger ID, survived, P-class, age, and fare, highlighting the mixed data types and some missing values, e.g., cabin. This preview sets the stage for understanding the variety and complexity of real-world data before applying data transformation techniques. Practice. Try printing out more rows to explore. Why transform features? Machine learning algorithms work best when all features are numbers. Values have a similar scale. Missing values are filled or removed. Let us look at feature scaling, normalization, and encoding in action. Running the cell now. Before we transform data, let us check for missing values. Missing information can hurt model performance. We quickly find out which columns have missing data. This helps us plan data cleaning steps. Running the cell now. This output shows the count of missing values in each column of the dataset, revealing that age, cabin, and embarked have significant gaps. Noticing these missing values is crucial before transforming features because models require complete numerical inputs, so we'll need to handle or impute these nulls to ensure the algorithm performs well. Now let us handle missing values in the age column. We use the median, which is the middle value, to fill blanks. We calculate the median age of all passengers. We replace empty age spots with this median value. Now there are no more missing ages. We check again to make sure the age column is filled. Running the cell now. This output shows that there are now 0 missing values in the age column, confirming that the median imputation successfully filled all gaps. This step is crucial because filling missing numerical values ensures that the feature is complete and can be effectively used by machine learning algorithms, aligning with our goal of preparing clean, numeric data. Normalization versus standardization. Normalization rescales features to a 0 to 1 range. Standardization changes features to have mean 0 and standard deviation 1. Normalization is good for algorithms that compare distances, like k-nearest neighbors. Standardization is common for most machine learning algorithms. Running the cell now. Next, let us choose columns with numbers that need scaling. Age and fair are both numeric and important for predictions. We make a list of columns with values to scale. We will use age and fair to show transformation. Here is a quick look at their current values. Running the cell now. Here we display the first few rows of the original numerical columns, age and fair, to observe their raw scales and ranges before any transformation. Noticing the wide range, especially in fair, highlights why normalization or standardization is necessary for consistent distance calculations in algorithms like KNN. This step sets the baseline for understanding how scaling methods adjust these features. Let us normalize the age and fair columns. We will use the Minute-Max Scaler tool to adjust values between 0 and 1. We import a scaling tool from scikit-learn. The scaler finds minimum and maximum values. Every value is shifted to fit between 0 and 1. We make a new, safe copy of our original data. We transform only age and fair, leaving other columns unchanged. Now age and fair are easy to compare and use. Running the cell now. The output shows the age and fair columns rescale to fall between 0 and 1, as indicated by the Minute-Max Scaler transformation. Notice how even larger original values are compressed into this narrow range, making features comparable on the same scale, an important step before using distance-based models like KNN. This confirms successful normalization, ensuring no feature disproportionately influences the model due to scale differences. Now let us try standardization. This makes each value show how far it is from the average, using the standard deviation. We use a different scaler for standardization. This method finds the mean and spread for each column. Values are now centered around 0. We use a fresh copy of our data to keep things safe. The transformed age and fair columns are now ready for many models. Take a look at the new values. Running the cell now. This output shows the first 5 rows of the age and fair columns after standardization, where the values are transformed to have a mean of 0 and a standard deviation of 1. Notice how the numbers now include negative and positive decimals instead of the original scales, reflecting this shift and scaling. This confirms that standardization centers the data and adjusts its spread, which is essential for algorithms sensitive to feature distributions. What about text columns? Most algorithms need numbers, not text or categories. We need to encode words into numbers. Types of encoding. Label encoding assigns an integer for each category. Hot encoding makes a column for each possible value. Let us try encoding the sex and embarked columns. Running the cell now. Let us use label encoding to turn sex into numbers. This step lets algorithms work with gender as a feature. We import a tool for label encoding. This tool assigns a number to each possible value in sex. We copy our data to avoid changing the original. Now, sex is represented as 0 or 1. This allows machine learning models to use it. See how the sex column is now all numbers. Running the cell now. This output shows the first 8 values of the sexed column after label encoding, where a male and a female have been converted to 1s and 0s. Notice how the original text categories are now numeric, which is essential because many algorithms require numerical input for computations. This step demonstrates encoding text data into numbers to prepare it for machine learning models. For embarked, let us use hot encoding. This creates a column for each boarding port. Each row has a 1 in the column that matches the passenger, and 0 in the others. We use a pandas function to create new columns for each port. Every passenger gets a 1 in just one of the new columns. This avoids suggesting any order between the locations. Check out how the new columns look now. Running the cell now. This output shows the result of one hot encoding the embarked text column, converting each port category into separate binary columns. Notice each row has exactly one true value, indicating the original embarkation point, which helps algorithms interpret categorical text as numerical features. This transformation is key when preparing data for models that require numeric input rather than raw text. In real projects, we want to automate preprocessing. We can do both scaling and encoding using a pipeline. This keeps everything in order and easier to reuse. We add a comment explaining the next step, combining scaling and encoding. We import column transformer to apply different transformations to columns. We import pipeline, a useful tool for chaining transformations and models. We define which columns are numeric features. We define which columns are categorical features. We assign the min-max scaler to handle numeric data scaling. We assign label encoder for encoding categorical labels, although this will be replaced later. We add a comment about needing a custom solution for label encoding in pipelines. We import NumPy as NP, which may help with array manipulations. We import base estimator and transformer mixin to create a custom transformer. We define a custom transformer class for label encoding inside pipelines. In the fit method, we create and fit label encoder on the input data. We return self to allow chaining. In the transform method, we transform input labels to encoded numbers and reshape for compatibility. We import one hot encoder to encode categorical features as one hot vectors. We create a column transformer that applies min-max scaler to numeric columns and one hot encoder to categorical columns. We prepare the data by selecting the numeric and categorical columns from the data frame. We fit and transform the selected columns using our preprocessor to get transformed features. We print the first 5 rows of the transformed feature set. Running the cell now. This output shows the first 5 rows after transforming numeric columns, age, fare, with min-max scaler to a 0 to 1 range, and categorical columns, sex, embarked, using one hot encoder into binary vectors. Notice how numeric values become decimals between 0 and 1, while categories expand into multiple binary columns, enabling algorithms to process text data as numbers. This demonstrates the key step of encoding text features to numeric form for model compatibility. Why is scaling important? If we skip scaling, some features can dominate others. For example, fare might have much larger numbers than age. This can confuse models like k-nearest neighbors or support vector machines, which use distances. Always check that your features are on similar ranges before modeling. Running the cell now. Let us put it all together in a mini project. We will clean, scale, encode, and split the data for modeling. We select important features for our small project. We import the function to split data into training and test sets. We specify the features we want to use. We create a copy of the data frame with just the selected features. We prepare to fill in missing values in the embarked column. We fill missing embarked entries with the most common value. We prepare to encode categorical features, sex and embarked. We convert sex from text to numbers using label encoding. We create new columns for each embarked category using one hot encoding. We prepare to scale numerical features age and fare. We initialize the scaler that will scale features between 0 and 1. We apply the scaler to age and fare columns. We assign the processed features to X. We assign the target variable survive to Y. We split the data into training and test sets for modeling. We display the shapes of the training data. We display the shapes of the test data. Running the cell now. The output shows the shapes of the train and test feature sets after scaling, encoding, and splitting the data. Notice that the feature matrix has 7 columns, reflecting the original features plus 1 hot encoded embarked categories and encoded secs. This confirms that the pre-processing pipeline correctly prepared the data for modeling, ensuring all features are scaled and encoded before splitting. Try exploring the mean values for your new features. Try normalization by hand to see how it works. We will turn these 5 numbers into values between 0 and 1. We start with a comment explaining the task. We create a list of numbers to normalize. We find the smallest number in the list. We find the largest number in the list. We use a list comprehension to apply normalization to each number. We print the original list. We print the normalized list. Running the cell now. This output shows how manual normalization scales the original data from its original range, 10 to 50, down to a 0 to 1 range. Notice how the relative spacing between values is preserved, but now all numbers are on the same scale, which prevents any feature from dominating due to larger magnitude. This illustrates the core reason for scaling, to ensure features like fare and age contribute equally in models. Now let us try normalization with your own numbers. We will read numbers as input and show you the normalized versions. Use a prompt explaining what to do, enter numbers to normalize. Read the input numbers as a single string. Split the string and convert each part into a float number. Find the smallest number in the list. Find the largest number in the list. Normalize each number to a value between 0 and 1 using minute-max scaling. Print out the list of normalized numbers. Running the cell now. This output shows the normalized values of the user-entered numbers, scaled between 0 and 1 based on the minimum and maximum inputs. Notice how the smallest number maps to 0.0 and the largest to 1.0, with others proportionally adjusted in between. This demonstrates how scaling prevents some features from dominating by bringing all values onto a common scale. YouTube call to action: if you like hands-on practice, subscribe for more beginner Python lessons. Tips for feature scaling. Always fit your scaler only on training data, not test data. Try different scalars if results look odd or slow to improve. Standardization works well for data with outliers. Normalize only the columns you need for your model. Remember, the right transformation can make or break your model. Running the cell now. Let us practice finding which columns are text or objects. This is useful before encoding features. We use a pandas function to get all columns that are not numbers. This helps us know what needs encoding. A list is printed for you to check. Running the cell now. This output identifies all non-numeric columns in the Titanic dataset, which include a name, sex, ticket, cabin, and embarked. Noticing these columns helps us decide which features need encoding or selective scaling before modeling. This step aligns with our lesson tip to normalize only necessary columns and avoid applying scalars to non-numeric data. Recap: what did you learn today? Why we transform features before modeling. How to handle missing values. How to normalize and standardize data. Different types of encoding for categories. Putting it all together in a pre-processing workflow. Data transformation makes machine learning possible and accurate. Running the cell now. Thanks for joining Week 3. Check out the description for more exercises and datasets. If you want to practice more, comment below with your questions or ideas. Subscribe for Week 4 and more data mining tutorials. Happy coding and keep learning. Running the cell now.